Okay, a very good afternoon, all of you. Just we started with microgrid, and now we know what we mean by the microgrid. Basically, it is a local energy grid which is having self-sufficient energy system which could work in discrete geographic footprint, particularly your college campus. It could be hospital complex, it could be a business center that we have seen. The objective of this microgrid is to ensure better energy reliability, security, efficiency. Then its characteristic, we talk about that it is a local, independent and intelligent microgrid. So that we discussed in previous lecture. So other characteristic which defines basically the microgrid, that is it provides sufficient and continuous energy. It should have its own intelligent, basically it should have some its own internal control and optimization strategy. It must be able to operate in islanded mode and able to reconnect to the main grid. It can also use as a flexible control. It is also applicable to various voltage levels, usually 1 to 20 kV, and it may have storage capacity. So basically we talked about what microgrid is and what microgrid is not. So basically we discussed that simple backup generator, that is not a microgrid, or simple distributed energy system like DZ. For example, you can think about solar rooftop panels, that is not microgrid. Individual generating unit, that is not a microgrid basically. So that we understood, then we come up with a microgrid. That is also we talk about that a group of individual generation sources that are not coordinated but run optimally for a narrowly defined load, that is also not a microgrid. A load or group of loads that cannot be easily separated from the grid are controlled, that is also not a microgrid. If something is connected to the grid but it cannot be operated in islanded mode independently, that is not a microgrid. So you can keep these things in your mind when you are defining a microgrid. So it can be basically connected and disconnected from the main grid. Then we also talked about the flow of energy, if it consists of various energies like fuel, electricity, losses, heats, that also we discuss. So you can take a quick recap through this diagram. Then okay, how it is connected, that it can be connected some common coupling where the voltage is maintained at the same level. So in this way you can connect with microgrid. Then we talked about the microgrid drivers. It include the environmental incentives, then cost effective access to electricity, reliability, security, energy efficiency. These are the drivers basically which motivates there should be the microgrid. These are the factors: environmental incentives, cost effectiveness, reliability, security, energy efficiency, renewable energy utilization, more and more renewable energy that should be integrated. It is helping basically. So microgrid is there. Then we talked about the benefit, and broadly we classified the microgrid benefit into economic benefit, environmental benefit and technical benefit. And we have seen that which benefits are applicable to which entity. Basically it is your distribution system operator. You can think about Mahavitran company, consumer, micro generation. It also promotes the micro generation. So micro generation, that is also considered as a benefit to the microgrid. So under technical benefit, there were peak load saving, voltage regulation, energy loss reduction and reliability enhancement. These are the technical benefit. And environment benefit, the reduction in greenhouse gases And in economic benefit, that will be to the load consumer benefit, then micro generation benefit, and network spending reduction benefit would be there. So that we discuss in little detail. Then we come across the microgrid categories, where it could be on the basis of where basically the microgrid is deployed. On that basis, we said it could be institutional microgrids, it can be commercial or industrial microgrid, it can be community microgrid, as well as the microgrid can be classified on the basis of different voltage level. So that we have seen. Today we are going to talk about basically the formation of microgrid, or you could call it as building blocks of a microgrid. So a microgrid that will consist of three things. One would be physical system, another will be the control system, and third one will be interface with the other system at the utility. So let us see one by one. Physical system in microgrid, it can largely composed of the physical components. It could be sensors, it could be switches, power electronics, energy storage devices, generators, protection equipment, metering devices. So broadly, if you think about what it could consist of, so it is the sensors. So why the sensors are needed? So sensors, you could say in more generally, information input are required to determine whether criteria for islanding or reconnecting that should be done. So sensors basically give you information. On that basis a decision can be made for whether microgrid should be operated in islanded mode or it should be remain connected with the grid. And once if it is started operating in islanded mode, then when it should be reconnected to the main grid. So basically here sensors can be considered as the eyes of the microgrid. So this will give you basically the information. On that basis the decision can be taken for operation of microgrid in islanded or grid connected mode. Then physical system, it will be having the switches. So these switches will be intelligent switches which will be considered as a vital part of microgrid. The reason for considering it as a vital part of microgrid is that it allows quick reconfiguration of the component in the microgrid. Reconfiguration means the things can be connected, disconnected. So when you are disconnecting something from a particular system, so it will be considered as a reconfigured, and you are connecting something. So these switches, intelligent switches, allow the microgrid to electrically disconnect or reconnect with the grid. A particular section of area of the circuit can be disconnected or reconnected, and it can be bring various distributed energy resources components on or offline. So if microgrid consists of your battery, it may consist of wind, solar. So a particular part can be connected, disconnected using these intelligent switches. Okay. The other thing which consists of microgrid, that will be the power electronics. So we know that the converter is important because it allows to convert power from DC to AC and AC to DC. This conversion is required, as well as there is need of voltage changes for distributed energy resources components, that is DER component. So when the power electronics converter would be there, so this is going to allow the distributed energy resources such as energy storage or micro turbine generators to be grid connected. Basically, nothing can be, any distributed generation cannot be directly connected to the main grid. At least the voltage and frequency criteria that should be met. The frequency that should be the same. So when you are generating in DC and you want to connect it connect the same with AC grid. Okay, so you need power in AC at the same frequency. If your grid is of 50 hertz, then you need the AC at 50 hertz, then it can be connected to the grid. So this capability will be provided by the conversion system, AC to DC conversion. So basically this is enabling the energy storage or whatever micro turbine generators can be to be grid connected despite non-grid conforming generating modes. Maybe it is not as per the grid requirement, but this is allowing, making it compatible, you could think in that way. The another part which consists of physical system, it could be energy storage. So energy storage, this is going to help smooth rapid changes due to external events are characteristic of DRs in the microgrid. See, when distributed energy resources we are talking about, particularly the renewable generation, it's characterized by uncertainty, variability, intermittency. So these are the characteristics. What it means that the generation is not constant, it is variable. Variability is there and uncertain, it is not predictable. Basically you cannot with sure shot say that okay, there will be a constant generation for this particular 1 hour. So there is variability. So at that time this energy storage might help the microgrid to remain connected with the main grid. So in this way, this energy storage would help basically whenever there is external events are characteristic of DR in the microgrid. The other example you could consider might be there is an event of blackout. So during this blackout, this energy storage, if the batteries are available with you or any hydro pump storage system is available with you, so this is going to support the system for few minutes with generator startup, because generator going to take some time. There is a startup time. For large generator it could be 5 hours, even greater than that 10 hours it requires for just starting generation. A small generator, maybe the starting time could be the 1 hour. So that particular time the energy supply can be maintained through the energy storage. So the storage, therefore the capacity of storage, it should be sufficient, large enough, and it should be respond quickly. Like the batteries, they can respond quickly. You are using UPS at home, within a minute or you can say fractions of seconds you are in position to basically get the backup power if battery is there. If generator is there, so it takes though it is automatic, it takes at least 1 minute to supply you, because these things take time. So if the energy storage is able to respond quickly, that will be an added feature to the microgrid system, and it should be sufficient. The other things is the generators. Generators can take a variety of forms, but are most commonly diesel generator. It could be natural gas based combustion engine generator. These generators are necessary, though renewable alternatives are available. The reason is that it provides consistent energy which can be relied on with relatively high certainty. Basically, renewables are uncertain. You cannot rely. But if diesel generator set is there, so you can be assured that okay, there is consistent power if the fuel is available with you, whatever petrol, diesel is available with you. But you cannot rely. That's why though renewable generators are there, along with that at least diesel or gas based generator should be available for it. May consist, basically it is not compulsory, but it is recommended that these generator should be the part of microgrid. Then protection equipment is required. Microgrid is there, it has controlling capability. It is going to control generator, load, etc. There is fault. When fault is there, so there will be rise in current. So what would happen? We need to protect equipment from this high fault current. Whole system must be protected basically. So protection equipment is needed. Protection equipment is always necessary regardless of whether or not the distributed energy resources is configured in microgrid. Whatever is the case, it is required. Special precaution is needed in a microgrid because of the added level of complexity involved with becoming a separate electrical entity. We know that microgrid can be operated in islanded mode or independent mode. So its protection becomes necessary because it has to operate in islanded mode. Specifically, there will be the major issues that must be accounted for protection when disconnecting and reconnecting with the grid. And there should be assurance or ensuring that there is an appropriate level of fault detection. Yes, there is a fault, so it must be detected, and protection in each part of the islanded microgrid system. Whenever there is fault, it should be disconnected. Control system for protection equipment will have to be modified to fit the operating paradigm of the microgrid because it can be operated in islanded as well as in connected mode. The other component which could be part of physical system or the microgrid, that will be the metering. Metering is required because the surplus power can be sold to the main grid. So how much power is supplied from microgrid to the main grid, and in certain condition some of the power can be obtained from the main grid, so its metering is required. So advanced metering that should be in place at the substation and preferably in the residential neighborhood so that condition and power flow can be monitored in real time. So metering is also going to help what is the condition and power flow in real time. If metering is there, means what is happening, whether power is drawing from main grid or it is sent to the main grid from the microgrid. So that can be also understood. The direction of flow of power can be monitored. That is also another purpose, condition basically. Then another part is the control system of the microgrid. For a microgrid category, you can consider multi-medium voltage feeder microgrid. In our classification, it is the last one, the D category. So three functional level of automation can be basically identified. One is local controller, necessary to control individual component of the microgrid. You can think about load controllers, energy storage controller, micro generation source controller. So these controllers response to orders sent by the microgrid controller. There are sub-controller basically. So this is going to respond from whenever the signal will be from the main controller. You can call it as the microgrid controller. And accordingly it is going to react in real-time condition. Suppose there is a fault is detected. So at that time a signal will be sent by the microcontroller to a sub-controller that okay, now you have to act. So this is going to give the guarantee the reliability of the different components. It can be achieved basically. Protection relays and smart switches are also part of this level of automation. We are talking about the load controllers. Local microgrid controller are going to provide real-time monitoring and control functions for all the components within a boundary. A boundary will be there, so in that boundary whatever components are coming, because local, we are saying the local microgrid controller, possibly there may be more than one. Its main objective of this local microgrid controller will be to ensure power reliability and quality. Power quality matters, reliability is required, so that is ensured by the local microgrid controller. It may bear some basic local optimization function based on economics of local generation and storage. See, the optimization is always done in order to achieve the economic of local generation. Means possibly suppose you are having the diesel generation unit, okay, and you are having the renewable generation. Your renewable generation is sufficient to meet the local demand. So, and at the same time, the surplus energy, the energy which is available from the diesel generation, that is surplus, and you are selling it. But the price at which it is stored, that is not beneficial. So this optimization function, what it will do, it will say instead of generating electricity from the diesel generator, stop it. Do not generate from the diesel generator because it is not economically beneficial. So that generation will be stopped using the optimization function, and the local demand will be met by your renewable generation. So this could be a possible case. Just for better understanding, we have considered this example. So local microgrid, it may have some local optimization function which will be based on economics of local generation and storage. The master microgrid management system will be there. We talked about local controllers, we talked about local microgrid controller. Now we are talking about the master microgrid management system. So this is going to allow optimizing the overall microgrid, complete as a whole microgrid or collection of microgrid. It may consist of a number of microgrids. Okay, there could be one microgrid, there could be 2, 3, 4, maybe a number of microgrids. So the master microgrid management system is going to allow optimizing the overall microgrid or collection of microgrids under its control. It defines set points for all the loads and generators to optimize the efficiency of the microgrid, which will depend on the electricity prices and local generation cost. Already we said, if suppose your microgrid that only consists of diesel generating unit, and the power which is available from the main grid, that is cheaper than what you are producing from the distributed generation or diesel generators. So it's better to purchase from, draw the power from the main grid instead of producing your. So that's why we are saying that it is going to optimize the efficiency of the microgrid, and the basis will be electricity price and local generation cost. If you are producing at lower cost, then purchasing power at higher price, then generate your own generation. If you are capable to meet the energy demand from your own generation, which is cheaper than the supply which is available from your Mahavitran company, then it is obvious to use this. If it is costlier, then purchase from there. If both are same, then that's fine, you can go with any. Finally, the master microgrid management system will be responsible for the disconnection or reconnection to the main grid. So this is a master management. Okay, there are two grids are operating under master, so it will decide whether both should be disconnected or one should be disconnected, or what should be done, which should be reconnected. So that decision will be taken by the master management system. It may also interact directly with the market or with curtailment service provider. Curtailment service provider, you could think it as aggregators, or you may also think it as system operator, distribution system operator. You may think about that, which are going to tell you, okay, now there is excess generation or there is less generation, so you curtail your load. We are not able to provide in case of less generation with the grid. So what they are going to tell the microgrid operator or controller, that we are not able to supply the demand required by you. So now it is recommended, now it is requested to curtail this much of power. So that request will be given by distribution system operator, or if some contract is done with certain aggregators, so on the command of aggregator this is going to happen. So this basically depends upon how the microgrid is participating in the market. It can directly participate or it can participate through some aggregator. So that could be a possible condition. So that decisions will be taken by your microgrid management system, or you can say microgrid operator, that is going to do, because we are particularly talking about the control system. So microgrid management system, if whenever command will be given, it is going to operate accordingly. So here you can see a possible microgrid automation architecture. You could see there is DMS, utility microgrid management. Basically for D topology, what we have considered the last one, the fourth category, for that it is shown. So distribution management system is there, which will be connected with solar forecast, wind forecast will be there. Basically forecasting means prediction on the basis of historical data. You can forecast it, you can predict it, okay, how much solar is available. So according to that, if sun rays is available, what would be your production depending upon the installed capacity. The same way the wind generation can be find out. Then there is master multiple microgrid management, MMGM, master or multiple microgrid management system will be there, which will be working in coordination with distribution management system. And then this microgrid management system is going to control your load controller, your microcontroller, micro source controller, then storage controller, then static smart switch. It will be controlled by master grid management system. It could be your master smart switch. There could be several master smart switch and static smart switch it would consist of. It is also going to control MGC, which will be again connected with this one MC, that is your microcontrollers, micro source controller and load controller. Several MGC would be there. So it could be industrial microgrid, intelligent building microgrid. There could be various things involved: wind turbine, PV, commercial, residential, battery, electric car. So it is basically giving you a possible microgrid automation architecture. So you will be having an idea that exactly how it is controlling. Then interface with other systems. That is part of again microgrid building block. The microgrid controller relies on other systems to deliver information to it. We already talked about IEDs, as well as executes some of its requests. Microgrid is connected with other systems. There are a number of systems, so certain information will be transferred to that system. Some information will be transferred from that system to microgrid. So maybe certain requests will be made, like the load curtailment. So some request is from there, so it should be done. Like there is fault, so some request should be there. In some cases, the utility can use its system to deliver commands to the microgrid controller. Though it can operate independently, the microgrid controller is of most use to the grid when it understands the external pressure on the system and reacts accordingly. What is the information? What they are saying? Basically, your distribution management system, or OMS, or automating metering infrastructure system, what they are telling, according to that, means whatever data it is sending, according to that it is going to take the decision. Particularly, just maybe there is a fault, so current would be high, so it should be disconnected somewhere. You can think in that way. So interface with other system is required, with other entity that is required. Let us talk about the microgrid general functions. The architecture earlier is functional. What it means that it may have to be adapted depending upon the size of the microgrid and the regulatory constraints. See, the microgrid can be installed or in a building, and a microgrid which is installed in another building, it may have a different size depending upon the resources of generation which is available and the power which a demand which has to be met by this installed microgrid. So size could be different. The other thing, there is a regulator, so it poses certain constraints. There are certain rules that, okay, if you are establishing a microgrid here, so it should abide by certain rules and regulations. You can only connect with the grid if you are having this much capacity. Might be, that could be one. For example, for instance, we are considering this could be one constraint. So there could be n number of constraints. In any case, it is mandatory that all functions are fulfilled somewhere in the microgrid. Manage exchange with the main grid, that is disconnection, reconnection, market functions, emergency control if required. So this should be managed basically. Operate reliability for microgrid consumers in islanded mode and in connected mode. Whether microgrid is connected, operating interconnected with main grid, or it is operating in islanded mode, reliability should be maintained for microgrid consumers. Means for that complex residential building or hospital, they must be continue with the supply. It must optimize asset utilization. Whatever assets it consists of, it could be your distributed generators, it could be your load, it could be transformers. So it should be optimally utilized, efficiently utilized within the microgrid, while in islanded mode or in connected mode. So that's why we said that there is some optimization algorithm or functions are there. So that is going to take care about that. If microgrid is operating in grid connected mode, so this is the best utilization of assets. And when it is connected in islanded mode, at that time this is the best utilization. So that is required. Asset utilization is required. Maybe this is constrained by some economic factors, that is possible. So in that case, considering all the constraints, considering that basically this will optimally utilize the asset, best utilization could be your optimal utilization, or maybe different. Then let us talk about protection issues of microgrid. We talked about microgrid can operate in islanded mode, it can operate in grid connected mode if suppose there is some fault. So the fault current, it is obvious that it will be different in both mode of operation, that is grid connected mode and in islanded mode. So this fault current that will be different. The short circuit power, that is also going to vary significantly. Fault, it causes loss of sensitivity, overcurrent, earth leakage, disconnection of generators. If fault is there, possibly there is some of generators that will be disconnected. Islanding, microgrid that will be disconnected from the grid and it will operate independently. So islanding. Reducing reach of overcurrent relay. Single phase connections, possibly 3-phase is there, so single phase connection would be there. And loss of stability. So these are the possible problems which could be due to a fault or faults. Depending upon location of faults with respect to distributed generators and existing protection equipment, problems like bidirectional power flow and change in voltage profile may also occur. Bidirectional power flow, maybe the power should flow from A to B, but it started flowing B to A. This is happening due to the fault, possibly. The voltage profile, receiving end voltage is greater than sending end voltage or something, maybe there is dip in the voltage, you have studied the voltage profiles. So that is possible. The power output of distributed generators, like it may consist of your synchronous generator, induction generators, inverter interface protection unit, that will be unpredictable. It will be due to which whenever there is a fault, power output of these DC sources changes. There is a fault, so power output that is going to change. So that is unpredictable basically. So broadly, if we say what are the key protection issues, so it will include modification in fault currents, that is grid connected and islanded mode, device discrimination, reduction in reach of impedance relays, reverse power flow, bidirectional power flow, what we were talking about, sympathetic tripping, islanding, single phase connection, selectivity. So these are issues what we discussed, that is summarized here. Let us talk about what would happen when your microgrid is connected in islanded grid connected mode. So when a fault occurs. So in this mode, during the occurrence of fault in microgrid, the protection device and distributed energy resources that must respond only after the activation of protective device provided at PCC, control center. With the fault ride through capability, the distributed energy resource should continue its work, it should not stop. For fault within the microgrid, the design protection strategy should disconnect the faulty portion from the rest of system that is known to us. It should happen basically. So according to the design, whatever protection strategy is there, so according to that, whatever faulty protection, it should be isolated from the healthy system. The conventional overcurrent protection scheme is set at a fault current of 10 to 50 times of the full load current. You could appreciate that the OC protection, that is 10 to 50 times of the full load current in grid connected mode. Some non-fault cases result in voltage unbalances which are difficult to identify. So there is a need for much effective protection scheme to avoid such unwanted situation. So some research is needed basically in order to avoid this non-fault cases. What would happen during islanded mode, faults during island mode? In this mode, the nature of issue is different from the previous case, means connected mode. We already said the fault current, that would be the different. So here the fault current, that will be 5 times the load current. In this case, the fault during islanded mode. So the overcurrent protection scheme is set to get activated at 2 to 10 times of the full load current. Here what we have shown that the overcurrent protection scheme that is set at a fault current of 10 to 50 times in grid connected mode. In islanded mode, it is 2 to 10 times only. So this is reduced 2 to 3 times the full load current of converter based DER resources in microgrid. This difference makes the uses of fuses rather than OC protection devices in the microgrid. So when the current is reduced, so what you can do, you can change the protection scheme. Basically you can go for the fuses instead of overcurrent protection devices, advanced devices in case of microgrids, but in islanded mode. That you should keep it in mind when it is designed. Changes in fault current magnitude. The fault current level is high in grid connected mode rather than islanded mode. So according to types of DG, the fault distributed generators, the fault current contribution is also going to vary. If DG is different, distributed generation is different, so your fault current, that will be different. Fault current of synchronous type DG is 5 times of that rated current, and inverter fed DG is 1.5 times. See the changes, 5 times and 1.5 times of the rated current. Therefore, prediction of fault current is difficult because the magnitude of fault current depends upon many parameters, including the mode of operation, types of DG and number of DG. Basically what we are trying to understand here, there will be change in the fault of current because the fault of current, that depends upon various factors, in which mode microgrid is operating, islanded, independent, which type of DG is there and how many DGs are there. So this is going to decide basically the fault current. That's why it becomes difficult to find out the change in the fault current magnitude. We are talking about the protection scheme or issues related to the protection of microgrid. So this is the issue. Okay. Reduction in reach of impedance relay. The occurrence of fault in downstream of the bus DG connected to utility grid. Impedance measured by relay located in upstream is higher than real fault impedance. So whatever impedance you are going to measure, that would be actually higher than real fault impedance. So this is going to affect grading of relays and it will cause delay in operation, or sometime possibly the relay is not going to operate. This is happening because of impedance what you are measuring, that is different what actually is set for a particular operation of the relay. So this is the problem with our issues with protection of microgrid. I think the things are clear to you. Bidirectional power flow, already we said there is flow of reverse power flow is possible. Unidirectional power flow take place in conventional distribution system. The interconnection of DGs in distribution and makes the power flow reverse. We said that surplus power can be sold. It means power flow that will be from microgrid to the main grid, that is the reverse flow of the power, and it leads to power quality issues. So what would happen when there is bidirectional power flow? So there may be issues with power quality, there is issues with voltage variation as well as protection issues, bidirectional flow. Accordingly, you need to set the relays or protection scheme should be designed. fault stripping. It occurs when a DG is located near to the substation in a feeder and if fault current in a healthy feeder is supplemented by the DG connected in neighboring feeder. Then the protection device in the healthy feeder may isolate the circuit unnecessarily. So this is happening, fault stripping is possible because of the location of the DG, you could say. Blinding of protection. When DG is connected to a network and a fault occurs in that feeder, the impedance of the grid is much higher than the actual DG impedance. So what would happen as a result? This makes the short circuit current less than the pickup current of the feeder relay. So consequently, it is going to lead to the failure in detection of the fault. So this is called the blinding of protection. So this is another issue with the protection issues of microgrid. Resynchronization. It is another issue with the protection. After islanding, the process of resynchronization is going to take place in order to reconnect the microgrid with the main grid. So this can be done either in manual mode or in automatic mode. The microgrid synchronization scheme, there are three types. One would be active synchronization, passive synchronization, open transition, transfer synchronization. So basically there could be a possible way can be selected for resynchronization out of these methods. Some of the issue already we discussed, stability issues, power quality, then intermittent output. Let us consider this. The renewable energy sources, solar, wind, they are intermittent in their power output because the availability of sources. It means the coordination between the DG and storage device is essential. It means that if higher power is generated, so surplus power can be stored to the energy storage devices. If there is low power generation, at that time the energy storage devices will supply the power, maybe in order to meet the demand or maybe if it is supplying to the grid. Okay, so that's why it should work in coordination. Otherwise, again, there will be challenges with matching the supply and demand. So here we are going to stop today. If you are having any questions, you may ask. Otherwise, we are going to stop.